In chemical reactions, it is important to consider not only the chemical properties of the reactants, but also the conditions under which the reaction occurs, and the equilibrium toward which it proceeds. The law of mass action says that the rate of chemical reaction at constant temperature depends only on the concentrations of the substances that influence the rate. The rate law is experimentally determined and can be used to predict the relationship between the rate of reaction and the concentrations of reactant. The relationship between the rate of a reaction and the concentrations of reactants is expressed by a rate law. For example, the rate of the gas phase decomposition of dinitrogen pentoxide is directly proportional to the concentration of N2O5. The expression for the rate law generally bears no relation to the reaction equation and must be determined experimentally. Generally, for a reaction of the form that is written below, with no intermediate steps, the rate law given by the following: rate is equal to K times A raised to A times B raised to B. The exponents A and B are usually, but not always, integers. Take note that the exponents bear no relations to the coefficients Na and Nb, because the rate of a reaction has dimensions of concentration per unit time. Dimensions of the rate constant K depend on the exponent of the concentration terms in the rate law. If P is the sum of the exponents of the concentration terms in the rate law, P is equal to A plus B plus N, then K has dimensions of concentration raised to 1 minus P over the time. For example, consider 2A plus B forms C. The reaction rate is expressed as a derivative of the concentration of reactant A, or product C, with respect to time t. In this reaction, 1 mole of C is produced from every 2 moles of A and 1 mole of B. The rate of this reaction may be described in terms of either the disappearance of reactants over time or the appearance of products over time. For the reaction below, the rate of reaction with respect to A is delta A over delta T. The rate with respect to B is negative delta B over delta T. And the rate with respect to C is delta C over delta T. Because the concentration of a reactant decreases during the reaction, a negative sign is placed before a rate that is expressed in terms of reactants to make the rate positive. The rate for each substance should be divided by its stoichiometric coefficient, as in what's written below. According to the stoichiometry of the reaction, A is used up twice as fast as B, and A is consumed twice as fast as C.